Now we have almost everything we need to write TinyML. There's just 2 remaining bits. First, I want to show you how to extend the structure of this binary expression evaluator to handle variables and values, because this is something that will help you implement the rest of TinyML. And then I want to go through the tasks that I give you for you to implement based on the initial structure. So what we had in the binary expression evaluator is that we had expressions. Those were either constants or binary operations with left and right sub-expressions. And then we had an evaluate function that was taking an expression and returning an int. We want to change this in 2 ways. The first thing that we need is to add some sort of data type that represents values. Because in TinyML, you can evaluate expressions to multiple different types of results. Some expressions will represent numbers. We will also have expressions that represent functions. So the lambda construct, the fun keyword in F#, that creates a function value. And when we evaluate this, we need to have a representation for functions. So we need to sort of return something else than just an int. And what we are going to return is a new data type that we define for values. That's one change. The other change is that we will also want to handle variables. And so what I've done here is that I added a new case to my expression for variables. Variables will just contain the string name of the variable. And when evaluating, we will need to have values for all the variables in scope. So the evaluate function will now take an expression and also a variable context, which is a map that has assignments for all the variables. So for every name of a variable, it will have the value. So let's see how we can actually implement this in our previous binary expression evaluator. So I have the binary expression evaluator here, and I said we will want to have values. And for now, I will only have one case. I will only have numerical values as the result. We will be adding more cases later on. And so what I need to do, one useful trick in F# is that I can add annotation to my evaluate function and say, I want this to return value. And now the IDE or the F# compiler tells me where I need to fix things. So first I need to fix things here, because when I have a constant, I just return a numerical value as the result. Now I have more problems here. So one problem here is that n1 and n2 are now values, not numbers anymore. And so I can't just call the F# plus or F# times with values as arguments. I will actually have to do some pattern matching here. So there's various ways I could do this. Maybe the nicest is to say I will pattern match on n1 and n2. And if both of these are numbers, number n2, then we can continue as before. But if at least one of those is not a number, then this doesn't work. I can't apply binary operator on things that are not numbers. In F#, this is something that the type system enforces. So in the second lab, where we will write type checker and type inference for TinyML, we will add the mechanism that makes sure these things can never happen at runtime. Now I have one more bug to fix, and that's the fact that now that we can do the numerical binary operator, we again have to wrap the result in a number and return it as a number. So now we added values, and I can evaluate my expression, and the result will be number 42. This isn't adding any new functionality, it's just restructuring the code so that later on things will be easier for us to add. The second thing that I wanted to add was variables. So again, here I'm going to add a variable, and variable, an expression will contain a variable name. So for example, maybe here in my expression, I could replace one of these arguments with variable. So this will now take a variable x. When I edit the case for a variable, the fsar type checker notices that I have not added handling for that case to my evaluate function. So it tells me I'm not handling the case variable, and this is something that I do need to add. And so what do we do if we have a variable with some name v? Well, this is where we need to add the variable context. So I'm going to add a context here, and this is one case where I'm going to use the type aliases. So I'm going to say variable context is a data type, which is a map with keys being strings, and the values stored in the map are going to be of this value type. And then in my function declaration, I can again add a type annotation and say this has to be a variable context. And then when I have variable, I can do try find and pattern match on this, and we will try to find this variable. When it is there and we have some value, we just return the value. If it's not there, then we are going to say unknown variable. So if I run all this, I did something wrong here. So what am I missing? I need to call evaluate recursively here to evaluate the left and right sub-expression. And when calling those, I need to give them the variable context. Here, the variable context doesn't change. The same variables are available in both sub-expressions. But you can already see that once we add variable bindings, we will need to construct a new variable context with the additional variable. So now that I define all of this, I can try evaluating my sample expression. And if I give it an empty map as my variable context, then it says unknown variable. That is what we were expecting. But if I replace this and say map of list and give it a list where x is mapped to the number 20, then the evaluation should proceed fine, and I get the result being 82. So this is now a binary expression evaluator that also has support for values. We will be adding different types of values later on, and has support for variables. And this will be your starting point for adding more TinyML features to this little interpreter. And how are you supposed to do that? So when you download the skeleton with the starting code, there will be multiple different files. Each of the files will have some code that's already there and some tasks for you. And the tasks, there's sort of detailed commands that tell you exactly where you need to add what you need to add. And the basic tasks for TinyML, there's 5 of them, or actually 4, because the first thing was writing the simple numerical evaluator as the starting point, and I've gone through that in these videos. So we already have that. What are your what do you need to add? So the first task, number 2, that's just extending the existing code a little bit, adding unary operator like minus in addition to the existing binary operators, and adding a conditional. The unary operators are relatively easy. The conditional is more interesting because you can try to sort of do this correctly and only evaluate the sub-expression that you actually need. In our case for binary expressions, we always evaluate both sub-expressions. In TinyML, we don't have booleans, we only have numbers, so treat one as true and any other number as false. The most interesting thing in TinyML is functions and function application. And so we want to add 2 bits of syntax, one for defining a function, like the fun keyword, and one for applying function. The fun keyword in particular, this is where you will have to do something clever, because you will need to extend the data type that represents possible values, because function is another possible value that we can evaluate too. And when constructing the function value, it also needs to capture the current variables to support this static lexical scoping. In the code sample, you will find the right data type for it, but you will still have to add the implementation. The task number 4 is adding let binding, and this you can do either directly or maybe sort of in a more interesting way by using this desugaring of treating lambda as a function declaration and application. And the last basic task is adding a simple data type. So we will just do tuples. Tuple is another kind of value which stores 2 different values. And they can be constructed from 2 expressions that we both evaluate. And they give me the first and the second element of a tuple. And we will also need some syntax, some primitive for deconstructing tuples into 2 variables. So those were the basic tasks. And there's also bonus and super tasks. The bonus tasks are the ones for which my sample solution includes the code. And in TinyML, there's a couple of them. The first bonus task is adding the union data type. And this is in many ways similar to tuples. We are going to need a new value. This time the value will just represent one of the cases, but you need to remember which case it was. We will need some constructs for creating them and deconstructing them. So this is going to be our very, very limited version of pattern matching. And the next bonus task is to add recursion so that you can construct recursive functions. This will require adding a little bit of laziness into our variable context, because when you're defining a recursive function, you have to be able to access the function before it is defined. So one way of resolving this cyclic reference is to make that store that in a lazy value in the variable context. And this is kind of already leading to the next more sophisticated, more complicated task, where if you just add 2 more values, one for units and one for lists, you will add enough of features to TinyML so that you can write basic functions for manipulating lists. So if you add these 3 things, you will have TinyML where you can encode lists, you can encode lists of numbers, and you can write recursive higher order functions like map for transforming lists. So that's the bonus tasks. And the extra additional things that you can explore if you want to have more fun with TinyML is implement the call by name semantics. So rather than evaluating arguments to values before passing them on to functions, we can change the definition of the variable context so that it doesn't store just values, but actually stores expressions. And then we're going to change, this is going to change the semantics of TinyML from this ML-like eager evaluation to the Haskell-like lazy evaluation. And the final thing that you can try is change the implementation so that it doesn't actually use the variable context, but follows this approach of formal operational semantics, where whenever I'm applying a function, I actually take the body of the function and replace all the occurrences of the variable with the actual argument. This is not going to be very practical. It's sort of more to understand how that formalism works, but it's a fun thing you can try. So with all of these, you will have a nice implementation of TinyML, and there are a couple of interesting things that very small implementation explores. It kind of points out that you have to distinguish between values and expressions, and for things like call by value, call by name, this actually makes a big difference. It is interesting to see how the recursive function definitions have to kind of work in a clever way with the variables in scope, because you are kind of defining a function that can be used from within itself. It also forces you to think about the variable scoping, because if we want to have lexical variable scoping, we have to implement the functions in a certain way. And when you look at tuples and unions as two data types, you might notice that there's this interesting symmetry between the constructors and destructors. Both because for both tuples and unions, you will need something to create them and something to decompose them, but also because the way tuples are kind of composed, you need two expressions as the input, whereas when you're decomposing a union, you need two expressions to produce the output. But when you take the first element of a tuple, you just need one expression, you just get one value, and when you're creating a union, you will just need one value. So there's this interesting sort of symmetry that has deeper formal meaning, but we get to explore this as part of our TinyML implementation.